Hello, welcome to the video. Uh, in this video, we'll be looking at section 6.6, where we're going to be solving exponential logarithmic equations. So, um, the question that they pose to us is how can you solve exponential and logarithmic equations? A couple things you can do. One is you can kind of utilize all of the tools that we have um, used in this chapter when it comes to manipulating the equations, where you can make make an equation into a log, or make it into standard form, or expand or condense a logarithm to help you solve certain equations. But uh, another thing that you can do is this, especially when it comes to exponential equations. All right, so exponential equations is simply this: is when you have a variable you're trying to solve in the exponent. Okay, so if if you have on both sides of the equation, you have the same base. So like it's this particular one, it says that we have 3 to the x power is equal to 3 to the fifth. Well, since they have the same base, we can just set the two exponents equal to each other and then solve. So in this particular instance, we can say, well, x equals 5. Um, so it's not always going to be that simple. You may have to manipulate one base or another, or possibly both, to get that particular result for that particular equation. So, for example, like part A right here, we have 100 raised to the x power equals 1/10 raised to the x minus 3 power. So what I want to do is I want to make both sides of the equation have the same base. Now there are several ways that you can go about doing this. And what I'm going to do is I am going to attempt to make both bases a value of 10. So looking on the left-hand side, I got this 100 raised to the x power. So what I'm going to do is I am going to manipulate this 100 to make it look like it is a 10. So with 100, I could say like, oh, can be 10 squared. And then it's raised to the x power. Using the power of power rule, I can multiply 2 to the x power. So now it is 10 to the 2x power. Looking on the left-hand side, because I already have 10 and it's in the denominator, what we can do, what we can do with that is I can change that as 10 to the negative 1. Because 10 to the negative 1 means that if you just put it in the denominator, it would be positive, and 10 to the first is 10. So now I can take this negative 1, and then this is also now going to be raised to the x minus 3 power. So I can now multiply x minus 3 over the negative 1. So it's essentially you're going to be distributing that. So now this is going to be equal to 10 to the negative x plus 3 when you distribute it. Now I have same base values of 10. Now that I have the same base values of 10, essentially I can forget about those bases and just look at the exponents and say, oh, this is going to be 2x equals negative x plus 3. And looking at this, I add x to both sides. So I got 3x is equal to 3. Divide 3 to both sides. X is going to equal 1. Now, looking at example B is a little bit more challenging because 2 and 7, I can't really manipulate that to um, become the same value per se. So what I am going to do is I am going to uh, change this into a logarithmic equation. So again, um, I'm going to say that this is log base 2 of 7 is going to be equal to x when I reverse bomb it. What I have here is I have this 7 and 2. If you recall from uh, the previous lesson in 6.5, we had the change of base formula. So what I'm going to do on the left-hand side is I'm going to use the change of base formula. Change of base formula says I'm just going to make this log of 7 divided by the log of 2, making my base 10. And this will then be equal to x. So now I can use my calculator and type in log base 7 divided by log, log of 2, log of 7 divided by log of 2, and I get my result about 2.807, and that'll equal to x. All right, so let's let's look at let's take a look at number 3. All right, so number 3 looks like a problem that I would assume you may not know how to solve right away, just because one, it has Euler's number, their natural base. So if we're going to go about solving this one, first thing I would do is let's isolate that variable e. All right, let's isolate Euler's number. So I'm going to add 7 to both sides. So now I got 4 times e to the negative 0.3x, and that's going to be equal to 20 divided by 4. So now I have e to the negative 0.3x is equal to 5. Okay, now again, let's look at this, and I would say let's put it into a logarithmic equation. So I have log base e of 5 is going to be equal to negative 0.3x. Now, if you recall from previous lessons, anytime we have something as a log base e, we can switch that to the natural log. So I'm going to switch this to the natural log of 5 is equal to negative 0.3x. Well, natural log is something that we can plug into our calculator. And if we plugged in natural log of 5, we get something close to 1.609. That equals negative 0.3x. Then we can simply divide that negative zero point 0.3 to both sides, which then means that x is going to equal a negative 5.365 about. And if you have additional questions on how to solve those other ones, let me know, and I'm more than happy to solve those for you. Here, same thing. When it comes to logarithmic equations, you can, as long as you have same base logs, you can then just set these two values equal to each other and then solve. Okay. So, so like in example A right here, I have natural log of 4x minus 7 is equal to the natural log of x plus 5. Since they're both natural logs, I can actually just get rid of the natural logs and say, oh, this is just going to be 4x minus 7 is equal to x plus 5. Okay, then I subtract x to both sides. So I got 3x over here. I'm going to add 7. That equals 12. Divide them by 3. X equals 4. So in this one, x would be 4. In part B, I have log base 2 of 5x minus 17 is equal to 3. Well, only one side has the log. All right, the other side just has a value of 3. So can't use that property, but what we can do is let's put it into exponential form. So let's bomb it. So my base is 2. My outside is 3, so it's going to be raised to the third power. And this is going to be equal to the middle, which is 5x minus 17. I can certainly solve this one. So 2 to the third power is 8. So I got 8 is equal to 5x minus 17. I add 17 to both sides. I get 25 is equal to 5x, dividing everything by 5x equals 5. In this example, we have two logs on the same side of the equal sign, and the result on the other side is not a logarithm, it's a constant, all right? The advantage is they're both the same number base, they're both base 10. So how we're going to go about solving this first is I just want to get it into one log. In order to do that, we have to condense it. So we have to resort back to our properties of logarithms. Because it's plus between them, we can rewrite it as a product. So this can be rewritten in condensed form as log of 2x times it by x minus 5, and that is going to be equal to 2. So now from here, I can distribute the 2x over the x minus 5. So this is log of 2x squared minus 10x is equal to 2. All right. Now, I think it's in our best interest to put it into um, exponential form and standard form. My base is 10, so 10 is going to be my base. It's going to be raised to the second power, and it's going to be equal to 2x squared minus 10x when I bomb it. Okay, so b is that outside is going to be the 2, and the middle is what it's equal to. All right. Because I have the x squared, it's a quadratic. In order to solve a quadratic, it has to be set equal to 0. So first thing I'm going to do is I'm going to take 10 squared, which is 100. And now I'll set this equal to 0. So I'm going to go 0 is equal to 2x squared minus 10x minus 100. To make things easier on us, I'm going to divide everything by 2 because they're all divisible by 2. So this is going to be 0 equals x squared minus 5x minus 50. All right, hopefully I can factor this, so I can go 0 equals parentheses, parentheses, x here, x here. They're going to be different signs because that second sign is uh, minus, so plus minus over here. Large numbers will be attached to the minus. There are two values give me product of 50, but their difference is 5. The answer is yes. It would be 10 over here with the minus and 5 over here with the plus. Zero product property tells me that x will be equal to negative 5 and x would be equal to positive 10. Because I have two solutions, it's in our best interest to check the solution. If I put in negative 5 in here, into the original equation, if I go 5 minus 5, or negative 5, what's here? Log of negative 10, I get like a non-real 0. So I get an extraneous solution here with x is 10. So the only one that works is, I get extraneous solution with x equals negative 5. The only one that works is x equals 10. and that is being able to solve exponential and logarithmic equations. I hope this helps. Till next time.